Yeah, you can.
Well, it's a great pleasure to have Kurt Hinterbichler, well, not here, but virtually here. And he's going to talk today about symmetries and anomalies of the IR fixed point of gravity.
All right. Thank you very much. So thank you for the invitation, and I apologize that I couldn't be there in person. We're still locked down here, so I hope to visit in person sometime in the future. So I'm going to talk about three different topics about the infrared fixed point of quantum gravity. So conformal versus scale invariance, one-form symmetries, and various anomalies. So this is work in collaboration with Kara Farnsworth, who's a postdoc here, and Andra Hulick, and then some upcoming stuff with Diego Hoffman at Amsterdam and Austin Joyce at Chicago and Greg Mathis at Cornell. So by way of introduction, here's the typical way we think of UV complete quantum field theories as a renormalization group flow. So if we have a quantum field theory, what's supposed to happen is that as we do a renormalization group transformation, which is just a change of scale, as we go from very short distances to very long distances, probing the theory, we are supposed to interpolate between scale invariant fixed points in the UV and the IR. So if I have, for example, a correlation function, if I look at it at where the points are very close together, they should take the form of a scale invariant theory, which is the UV theory. And then as you make them very, very far apart, they should interpolate, and as they become very far apart, it should again take a scale invariant form of an infrared scale invariant theory. So the endpoints of this flow, by definition, are scale invariant theories. So they have a symmetry where they're invariant under a change of scale. So this is the typical scale transformation when it's acting on a local field. And the fields scale according to some scaling weight, which is basically just the engineering dimension of the field or the local operator. So the endpoints of the RG flow have this by definition. But what often happens is when we look at these endpoint theories, there's often an enhancement. There's a larger symmetry than just the scale symmetry and the Poincare symmetry that's already there. And that's the full conformal symmetry, which includes, in addition, these so-called special conformal transformations that take this form here. So this enhancement, it's been proven that in 2 dimensions, if I have a unitary theory with a stress tensor, if you have scale invariance, it automatically implies that you have this full conformal invariance. This hasn't yet been fully proven in dimension greater than 2, although there are some partial results. So perturbatively, you can prove certain things, and under certain assumptions about the stress tensor, you can prove it, but it's not been completely proven. And in fact, there are some counterexamples in higher dimensions for certain free theories. So the most famous counterexample is just free. Question?
Oh, so like for registration, I just like to.
Yeah, maybe you can. No, I think it's a noise from outside.
Oh, okay. Yeah. So a famous counterexample is just take the free theory of electromagnetism. So the action is just F mu nu squared, where F mu nu is the field strength of some spin 1. This action in any dimension is scale invariant, because a free theory in any dimension is scale invariant if you let the field transform with the right scaling weight. But if you do the special conformal transformations, if you transform the vector field in the manner that we showed before, so assuming that it transforms in the usual way under conformal transformations, what you get is some variation that's proportional to d minus 4. So in dimensions different from 4, this thing is not invariant under the special conformal transformation. So it's naively an example of a scale but not conformally invariant theory, whereas in d equals 4, it is fully conformally invariant. And you can confirm that by computing correlators of F mu nu, so gauge invariant correlators in the theory. You can show that these take the conformally invariant form in d equals 4, but not in dimensions greater than 4. Okay, so we want to study this issue for gravity. So how do we think about the renormalization group flow for quantum gravity. So gravity is not supposed to be a traditional quantum field theory. For one thing, there are not supposed to be local operators in quantum gravity. But there are other observables. So, for example, quantum gravity on flat space is supposed to have a well-defined S matrix that should be an observable that you can compute at all energies. So you can ask about the RG flow of the S matrix, for example. And all the mysteries of quantum gravity that we worry about are associated with what's going on in the UV. So what this UV part of the RG flow looks like. So if you believe, for example, the asymptotic safety people, then there should be some fixed point here in the UV, whereas in string theory, it's something else more complicated. But then you can ask, what about in the infrared? So if I go very far in the infrared, it should also approach some scale invariant theory. And the infrared we should know all about because we think we know what gravity is doing at long distances. We don't have to worry about quantum gravity or what's going on at very short distances. So at low energies, we know what the effective field theory for quantum gravity is supposed to look like. So if I take gravity and couple it to any massive matter and then integrate out the matter and look at low energies, the effective field theory is the Einstein-Hilbert action, which is the two derivative part, plus the higher derivative corrections, which are suppressed by mass scales corresponding to the massive stuff that I've integrated out. So if you look at very, very low energies, the only scales that are here are the Planck mass and whatever mass scales of stuff that you've integrated out. All these mass scales are going to infinity in the very, very far infrared. And so the fixed point that you reach is just the free theory of the massless graviton, which is the Fierz-Pauli theory, so the linearized theory of general relativity. So the field here is the symmetric tensor h mu nu, which is just the fluctuation of the metric around flat space. And this theory has a gauge symmetry, which is the linearized remnant of the diffeomorphisms of the full Einstein-Hilbert gravity. And this theory is now manifestly scale invariant. So h here, the graviton fluctuation, transforms with a scaling weight just given by its engineering dimension in this action, and that's the scale invariance that's there at the IR limit of quantum gravity. So we can now ask, what about conformal symmetry at this limit? And if you try to do the naive thing of just varying this h by the form of the special conformal transformations that we wrote down before, what you find is that the variation is proportional to d minus 2. And in d equals 2, this action is actually a total derivative. It's trivial. There's nothing going on in d equals 2. So actually in any dimension, this would seem to be another example of a scale but not conformally invariant field theory. What we're going to see is that this is deceptive and that in d equals 4, this is actually secretly conformally invariant still. So let's think about what are we actually computing at in this IR fixed point theory. So what are the local operators? So full quantum gravity is not supposed to have any true local operators, but the linearized theory does have local operators. So in the strict IR limit, we can talk about local operators. So the basic gauge invariant operator is the Weyl tensor. This is the analog of the field strength for electromagnetism. And this is the basic gauge invariant operator. So it's invariant under those linearized diffeomorphism symmetries. So here it is. It's made out of two derivatives of h, and this is some projection operator, which ensures that it has the symmetries of the Weyl tensor. So this is the Young tableau that corresponds to the index symmetries, so that it's anti-symmetric in the first two, anti-symmetric in the last two, and vanishes if you anti-symmetrize over any three. Those are the symmetries of the Riemann tensor. It's also fully traceless. The traceless part is the true local operator. The trace part we don't care about because the Ricci tensor is the trace part, and the Ricci tensor just vanishes on shell by the equations of motion. So that's not a true local operator. It's the Weyl tensor that's the true local operator that we're going to be interested in. This operator satisfies two equations of motion, which you can show just from the linearized equations. So it satisfies a conservation condition. If I hit any of the indices with take the divergence, it vanishes, and it satisfies a dual conservation condition, which is just the Bianchi identity, the differential Bianchi identity at linear order. And all other local operators, which are gauge invariant, you can construct just by taking products and derivatives of this basic Weil operator modulo these relations. Okay, so that's what we're going to be interested in computing. So as we already mentioned, in d equals 2, this Lagrangian is a total derivative, so it's nothing to study there. In d equals 3, the Weil tensor is trivial because the full Riemann tensor is determined by the Ricci tensor in d equals 3. So there's actually no true local operators in this sense in d equals 3. It's a topological theory. So we're going to be only considering dimensions 4 and greater from now on.
Can I ask, is it meaningful to wonder what would happen if I considered, say, like the first correction to linearized gravity? Like,
yeah, that's a good question, which I'll come back to that at the end. Yeah.
Okay. All right.
I also have a question.
Yeah.
If you consider like de Sitter or anti-de Sitter space with curvature, how this infrared limit works out?
Yeah. Yeah, that's a good question too. So I mean, there should be a kind of scale invariance that survives because the de Sitter as a manifold also has, you can consider conformal killing vectors of de Sitter space, and there's the same number of them as there would be on flat space. So you should be able to run this story also on de Sitter or anti-de Sitter. Yeah. Okay, so this Weil operator is what we're going to be considering. So its dimension here is d over 2 plus 1 because it's made out of two derivatives of h, which had dimension d over 2 minus 1. We can already see some peculiar things about this as a field theory. So for one, there's no true stress tensor operator because a stress tensor would have to be a dimension d symmetric tensor. And there's no way to make a dimension d symmetric tensor out of this Weil operator. So if I wanted to use just one power of w, I would have to take some derivatives to get rid of the indices to make it into a symmetric tensor. And there's no way to take derivatives without it vanishing in such a way to make a symmetric tensor. And if you try to use more than one w to contract the indices among each other to make a symmetric tensor, then your dimension will be too large. So there's no true gauge invariant local operator, which you can call a stress tensor in this theory. You may wonder then, where does the actual Poincare symmetry come from? And we'll see where that comes from later. There's also no marginal or relevant scalar operators. So scalar operators with dimension less than or equal to d, because you can't make a scalar from derivatives of w. And if you try to use more than one of these w operators, you'll have too large a dimension. So what that tells you is that, suppose you wanted to use this scale invariant theory as the UV fixed point of something. So you wanted to try to deform it by relevant operators like we typically do to generate an RG flow that takes you to some new IR fixed point. You can't do that here because there are no relevant operators that you can actually deform with. So this picture where you have linear gravity in the UV isn't allowed in the usual way. Okay, so we want to compute correlators of this Weil operator. So to do that, we have to gauge fix the action to deal with the linearized gauge invariance. So we do that in the usual way with the Fadeev-Popov procedure, and the ghosts decouple and you can ignore them. And what you end up with is this. So here's the linearized Einstein-Hilbert action now with this gauge fixing term introduced. So this, now we've introduced the most general possible way of gauge fixing at the quadratic level with two derivatives, and that maintains Lorentz invariance. And there's actually two different gauge fixing parameters you can have, which we've called Xi1 and Xi2. And the correlators of the W are, of course, independent of the gauge fixing parameters because they're gauge invariant operators. There's one value of this gauge fixing parameter which is not allowed, which is Xi equals 2, and that's not allowed because this value happens to not fully fix the gauge. There's a residual gauge invariance for this value, which looks like this, the double derivative of some scalar, which is enough to make the propagator not invertible. So we have to steer clear of this value Xi equals 2, but any other values are allowed. Okay, so let's first consider the case where D is greater than 4. So when D is greater than 4, there's a convenient choice for these gauge parameters, which is this here. So this doesn't work for D equals 4 because that would give this not allowed value of C2 equals 2. So if I write down the action for this choice of parameters, it looks like this here, where I've decomposed the metric perturbation into a trace-free part and a trace, which we've called phi. So we get now this action, and this action now happens to be fully conformally invariant. So if I do a normal conformal transformation, a special conformal transformation on this H and this phi, treating them like conformal primaries, this action is actually fully conformally invariant. So these are fields of weight d over 2 minus 1. So if I were to compute correlators of this H and this phi, they take the standard conformally invariant form. So here is the standard conformally invariant form for the two trace parts here. So there's some coefficient here, which you can calculate. And here's the standard conformally invariant form for symmetric traceless tensor. So it involves this index structure here, which involves this combination I, which is the standard kind of thing you see in conformally invariant correlators. And then there's no conformally invariant coupling possible between different spins. So if I think of this H and this phi as actual fields in the theory, so I'm not allowed to do these because these are not gauge invariant fields, so I shouldn't really think of these as being in the theory. But if I pretend that they are in the theory, so I extend the theory to include this H and phi, then it's now a conformal field theory. But it's a conformal field theory which is not unitary because this symmetric tensor, this H mu nu, violates the unitarity bound for a spin 2 in a conformal field theory. So it's not a unitary theory, but that's okay. That we shouldn't really be considering this as an operator. If we compute the correlators of the actual gauge invariant operator, it takes now the form of a descendant if I were to think of a descendant operator in a conformal field theory, that's the form that W takes. But it's not, of course, it's not a true descendant because it's not the derivative of any actual gauge invariant operator. So you can show that it satisfies all the proper conservation conditions that we had for the curvature tensor on shell. So here's the situation we have. The original theory is the unitary theory where we consider only the gauge invariant operators. And this is scale invariant, but not conformal because this 2-point function doesn't take the conformally invariant form. It's scale invariant, but it doesn't have the full conformally invariant structure. But we see that it's possible to extend the theory into a larger conformal field theory by including the actual original tensor in this conformally gauge fixed form. And this non-unitary, this larger conformal field theory is non-unitary. So we've embedded the unitary scale invariant theory into this larger non-unitary conformal field theory. So this same thing happens for electromagnetism, by the way. If you consider electromagnetism in dimension greater than 4, the correlators of the gauge invariant F mu nu operator are all they're scale invariant but not unitary. They're unitary, scale invariant but not conformal. But by including the actual gauge field A with a conformally invariant choice of the gauge fixing parameter, you embed it into a larger non-unitary conformal theory. Okay, so that's the story for D greater than 4. For D equals 4, we can't reach that conformal gauge that we were using. We can just use any other gauge and we can compute the 2-point function of the Weil operator. And what you find is that miraculously, the 2-point function does maintain its conformally, it gives you the correct conformally invariant form. So it gives you the correct form for this W being a conformal primary of dimension 3 in 4 dimensions. And this doesn't come out immediately. You have to use all kinds of complicated dimension-dependent identities that only work in D equals 4. So this W is actually a conformal primary, and this is enough to say that the full theory is now conformal because it's a free theory, so all the other correlators are determined by Witt contractions. They're all going to have the proper conformally invariant form. So a W of this dimension, in fact, saturates a unitarity bound for operators of its symmetry type, which is this here. And the conservation conditions that W has to satisfy, in fact, follow from the fact that you're right on this unitarity bound. When you saturate unitarity bounds, you get conserved tensors in conformal field theories. So these conservation conditions follow directly from the conformal algebra, and these are conformally invariant equations in D equals 4. Okay, so we can conclude that in D equals 4, linear gravity is actually a conformal field theory, even though the action is not invariant. You can't see this directly from the action just by varying h, like the way you could in electromagnetism. So whatever the conformal symmetry is, it acts in the action in some much more non-standard, complicated way that we haven't fully figured out yet. This same story should also apply to the higher spins. So if I consider a spin S gauge field, it's some symmetric tensor with S indices. It has some gauge symmetry where H changes by one derivative of some symmetric tensor with S-1 indices. Then there's some gauge invariant field strength, which is the analog of the Weil tensor, which has S derivatives and has the symmetries of a 2-row Young tableau. So it has S sets of antisymmetric indices. So we can figure out like the scaling dimension of these field strengths and the unitarity bounds of this operator, and they coincide exactly in D equals 4. So the conservation equations that have to be satisfied are in fact conformally invariant when D equals 4. So for all the higher spins, you should have a conformal theory in D equals 4 and a scale, but not conformal theory in D greater than 4 that we think should be embeddable into a larger non-unitary CFT by including the gauge field in the same kind of way. Okay, so I now want to go on to other types of symmetries that are present in this linearized field. And these are going to be generalized symmetries. So the usual global symmetries that we think about from Noether's theorem and stuff like that is that you have some conserved current that's associated with the symmetry. And then you can get the action of the symmetry by taking that conserved current, integrating it over a surface, and that gives you an operator, like a surface operator that you can wrap local operators with this surface operator, and that tells you how the local operators change under the symmetry. So these higher form generalized symmetries are just generalizations of this to other types of operators, like line operators and other different codimensions of operators. So we're going to be interested in these one-form generalized symmetries, where the current that you have is a two-form current, so some antisymmetric J mu nu, which is conserved on shell like this. And if you have such a current, you can make a conserved charge where you integrate the dual of that current over a surface. And the object that is supposed to be charged under this is now a line operator of some sort. So you have some line operator which carries some charge Q, and you can figure out what that charge is by wrapping the line with this surface operator, and that should spit out what the charge is. And the conservation of this current tells you that the charge should not care about small deformations of this surface. Any way that you wrap the line operator gives you the same value of the charge. So the standard example of this is in E&M. So in electromagnetism in 4 dimensions, you have 2 different one-form symmetries. So there are 2 different conserved currents of this type. There's just the field strength itself, F mu nu, which is conserved by virtue of Maxwell's equations in the absence of charges. And then you have the magnetic current, which is just the dual of F mu nu, which is also conserved by virtue of the Bianchi identity on F. So for each of these 2-form currents, you can make a charge where you wrap some line operator with a 2 surface. So there's an electric and a magnetic charge, which are the standard electric charge and magnetic charges that you have for charged objects in electromagnetism. So the standard solution that's charged under these is for the electric charge is just the Coulomb charge. So if I have a point particle, its world line is a line operator that carries some charge, and I pick up that charge by integrating F mu nu dual around it. And then the standard magnetically charged solution is the Dirac monopole, which you can't write globally in terms of the gauge potential. You have to use different gauge potentials in different patches and then glue them together by a gauge transformation. But the F mu nu is everywhere smooth, and when you integrate it around the surface, you pick up the magnetic charge. Okay, so in linearized gravity, we're going to have things that are similar to this. So we have this operator, the Weyl operator, which has 4 indices with the symmetries of the Weyl tensor. So what we can do is soak up 2 of these indices by contracting it with something like a killing tensor. And then what's left is going to be a 2-form current. If we want that 2-form current to be conserved, so W here is automatically conserved, but if I hit J with the derivative, it's going to hit this object, this killing tensor object. So if we want this thing to vanish, this killing tensor object has to vanish when contracted against W in this way. And due to the symmetries and the tracelessness of W, only the mixed symmetry traceless part of this term here has to vanish. So we get a kind of killing equation that has to be satisfied by this anti-symmetric tensor killing tensor. So this equation is like a generalization of the conformal killing equation. It tells you that some symmetry component of the traceless part of the first derivative of this thing has to vanish. And you can ask for solutions of this, just like you ask for solutions of the killing equations and get killing vectors, or the conformal killing equations, to get the larger set of conformal killing vectors. And the solutions of this equation are sometimes called killing nanotensors. So here's the general solution, where I've written this now in some D+2 dimensional embedding space, which is convenient when you're talking about conformal quantities. So these x's are coordinates in some larger embedding space, and this k is some antisymmetric constant tensor in the embedding space. And this k parameterizes the various solutions of this. So if I bring this down to the ordinary space by dimensionally reducing down to the actual d-dimensional spacetime, this higher dimensional antisymmetric tensor breaks up into a lower dimensional antisymmetric 3 tensor, 2 different antisymmetric 2 tensors, and a vector. So here, written out now in the ordinary 4-dimensional coordinates, is the general solution for what this killing tensor can be. So it has these free constant coefficients, one of which is an antisymmetric 3 tensor, 2 different antisymmetric 2 tensors, and 1 vector worth of parameters. So in d = 4, if we count all the different independent components of these things, there's 20 of them, 20 independent components in d = 4. So what we have is 20 different 1-form currents that are all going to give 1-form symmetries in linearized gravity. We can also package these in terms of dual currents if we're working in d = 4, because you can write down the dual of the Weyl tensor, where you dualize with respect to the first 2 indices, and that will give you some set of dual charges, because the dual Weyl tensor is also conserved by virtue of the Bianchi identity that the Weyl tensor also satisfies. Okay, so here's what physically these various 1-form charges are. So if I look at this component that was a vector's worth of parameters, the physical quantity that this picks up is in fact the energy momentum. So in linearized gravity, energy momentum is not a standard symmetry the way it is in ordinary field theory. It doesn't come from integrating a stress tensor, a local operator. It instead appears as a 1-form symmetry in this way. So the solution, which is charged under this, is just the linearized form of the standard Schwarzschild metric. That's the thing that carries mass or energy. So if I take the linearized Schwarzschild metric and I integrate it along it with this surface operator, where I turn on this particular component of the killing vector, it'll pick up the mass, so the Schwarzschild solution. And it will be, of course, it'll be independent of how I arrange the surface and so on. The 3-index thing here, if I dualize that in 4 dimensions, it picks up another vector. That other vector is a dual energy momentum. So this is sometimes called the TAMU charge in general relativity. So it's kind of like a dual to, like a magnetic dual to energy and momentum. And there's a metric, linearized metric you can write for that. And just like the monopole solution, you can't write it globally in terms of the actual metric tensor h mu nu. Only the curvature is actually globally defined. And the metric is you have to define it in 2 different patches, which are glued together by a diffeomorphism, which is the gauge symmetry at play. So now the antisymmetric component here is going to be the picking up angular momentum. So that's the charged solution under that is just the Kerr metric, which has rotation. So you can pick up the angular momentum of the Kerr metric by integrating a 2-surface this particular component. And then the other 2-index antisymmetric thing is like a dual to angular momentum. And the charge solution there is called the C metric. So these, we've been working in linearized gravity, so these are all linearized solutions, but in fact, these solutions all exist non-linearly as well. There's a full non-linear Schwarzschild and TAMU and Kerr and C-metric solutions. So that's one clue that it may not be stupid to consider these, that it's, these aren't just an artifact of the linearized theory, that they might play some role beyond just the linearized fixed point. The advantage of these things also is that they are everything here is manifestly gauge invariant, at least at the linearized level. All of these charges are integrals of gauge invariant local currents, the Weyl tensor integrated against these killing type tensors. So this is unlike the standard ADM way of doing it, where you have these ADM charges, which are surface integrals at infinity, which are integrals of non-invariant quantities.
Maybe this is a stupid question, but is this like an extremal Kerr metric?
No, because there's no.
Maybe I'm thinking of this wrong.
Yeah, I don't think so, because at the linearized level, I don't think you even see any extremality condition. You can have whatever charge you want. Yeah. So something must change when you go to the full nonlinear thing that enforces extremality. Yeah. Okay, so when we have symmetries of any type or conserved operators, we should ask about what anomalies might be present among these symmetries. And we're going to see that in this case, there are novel types of anomalies that these symmetries carry. So let me introduce the way we're going to be thinking about anomalies here. So one of the simplest examples of an anomaly in a quantum field theory is the following. So suppose that I have in 2 dimensions a spin 1 delta equals 1 primary operator in a conformal field theory. So some vector operator with weight delta equals 1, and the conformal algebra in D equals 2 tells you that this operator satisfies 2 different conservation conditions. It has to be conserved, it's basically because it's saturating this unitarity bound, but it also has to be dual conserved in this sense. So often people think of this as there's some dual current which is conserved. So for example, like if I have a fermion in 2 dimensions, you often talk about the ordinary vector charge and the axial charge, and these things are both conserved, but in fact, they're both related by a duality transformation. So really, there's one current that satisfies these 2 different conservation conditions. So if I look at the 2-point function, at separated points, 2-point functions are completely fixed by conformal invariance. So the form of the 2-point function at separated points is completely fixed to be this. And this satisfies, as it must, both of these conservation conditions at separated points. Okay, but in quantum field theory, correlation functions are supposed to be distributions. They're supposed to make sense when you integrate them against smooth functions, which are supposed to be like detectors. So they're supposed to be defined everywhere, including what's going on at coincident points. You're supposed to be able to integrate over them at coincident points. So we have to ask what's going on at coincident points as well. And the most convenient way to do this usually is to take a Fourier transform. So when we Fourier transform this conformally invariant form of the operator, we get this part here, which is non-analytic in the momenta, which captures everything that's going on at separated points. But then there can also be contact terms, which are analytic in the momenta. And these contact terms are supposed to parameterize what's going on at the coincident points. So we leave these analytic contact terms with some arbitrary coefficient to parameterize our ignorance about what's going on at the coincident point. So here, this is in the case of these two vector operators, this is the only possible contact term that has the right scaling symmetry of the rest of the stuff. There can be no powers of p, so it has to be just a constant, and it has to be proportional to delta. That's the only thing that's allowed. So there's one possible contact term with this arbitrary coefficient that we parameterized with C. So now we try to impose the conservation conditions, and we try to impose them everywhere, including at coincident points. And what we find is this. So it's the ordinary conservation gives this, and the dual conservation gives this. So for a generic value of this C, these things both fail to be conserved, but the failure is analytic in momentum. So the failure is local in momentum space, which means that it's localized to a delta function in position space. So the failure is happening only at coincident points, which as we saw before, at separated points, the conservation conditions are both fine. And the anomaly is just the statement that there's no choice of what this contact term can be that makes both of these things conserved. So I can choose C to be minus pi, and then it'll be conserved everywhere, but it won't be dual conserved at the coincident points. Or alternately, I can choose C equals 0, and then it'll be dual conserved, but it won't be conserved. There's no choice that makes both conservations hold simultaneously. And that's the anomaly. Okay, so often the way people frame this is in terms of an effective action. So if we're interested in computing correlators, we can couple we can write an effective action by coupling the current to some external gauge field A, and that gives us a generating functional where we can compute correlators by taking functional derivatives with respect to A. And now the conservation conditions on A show up as gauge invariances of this effective action. So the ordinary conservation current, the conservation condition on this current J shows up as a ordinary gauge transformation like this on the scalar gauge parameter on the gauge field A, because if I plug in A equals d mu lambda here and integrate by parts, that'll be the conservation of J. The dual conservation appears as this kind of gauge symmetry with some anti-symmetric gauge parameter, because if I plug this in for delta A up here and integrate by parts, that'll be the dual conservation condition on J that I'm looking for. So the effective action, we're going to be doing some path integral or whatever over the conformal fields. The effective action is only well defined up to local terms in this external gauge field. And these local terms in the external gauge field parameterize precisely these contact terms that we have to add at coincident points to parameterize what's going on there. So in this case of our two-dimensional vector current, there's one possible contact term, which is just A squared, and that comes with some arbitrary coefficient, which is roughly the same coefficient that we had in the possible contact term in momentum space before. So now the statement is that you can choose this C to preserve one of these gauge invariances or the other, but not both. So the anomaly in this language shows up as the failure to impose both of these gauge symmetries at the same time on the effective action. Okay, so here's a simple example of this. Let's just take a free massless scalar. And the free massless scalar, in fact, I can be in any dimension here. There's a current, which is d mu phi. And this current is conserved because if I hit this with the derivative, I get box phi, which is 0 by the equation of motion. And it's also dual conserved because if I hit it in symmetry, the derivatives commute. So this is a current, which should satisfy these properties that we're talking about. So now let's couple this theory to the current. So here is, we add to the action now this coupling to the external gauge field through the current like this, and then we add the possible contact term C. And now we can just look for these gauge symmetries. So if I look for ordinary gauge invariance, so we have to also be careful to allow the actual field itself to possibly transform under the gauge symmetry. So the only possible transformation that phi could have is a shift by the scalar lambda. And there could be an arbitrary coefficient out front, which is fixed to be 1 by demanding the symmetry. So the variation in S, the variation in the action comes out to be this, which tells us that the derivative of the current is this, proportional to C plus 1. So if I choose C to be minus 1, then this current will be conserved in the presence of this external gauge field. If I look now at the dual gauge invariance by this antisymmetric thing, there's no way the field can transform. The variation of the action looks like this. So the dual conservation looks like this. So there's no choice of C that allows me to maintain both gauge symmetries. I can choose one or the other. Whichever one I choose, the other is then completely fixed. And that's what we call the anomaly equation. We can also turn this argument around. So there's an interesting argument in this paper here, which says that suppose all I know is the anomaly equation. This is a new way of thinking about the Goldstone theorem. So because there's an intricate relationship between these anomalies and Goldstone particles. So suppose that all I have is an anomaly equation. So I know that there exists some conserved current that is conserved in the presence of background fields, but fails to have dual conservation by some amount that I know, this A. So this would be related to what I picked C to be just in the last slide. So now look at the 2-point function. So now forgetting about conformal symmetry or not knowing anything about the quantum field theory, I can write just the most general possible form using just Lorentz invariance of what the 2-point function can be. So it's this. There's only 2 possible Lorentz structures that can appear multiplied by some arbitrary functions of p squared. I can now impose these conservation conditions. So if I impose exact conservation on the current, it tells me that these 2 functions are related to each other. And then if I impose this anomaly equation, so I take one functional derivative here and see what that implies for the 2-point function, it tells me this, and then that fixes what this arbitrary function g has to be. So the form of the 2-point function is actually completely fixed by this anomaly equation. And then you can go and you say, let's look at some Lehmann-Chalane spectral decomposition of this 2-point function and ask what particles are present in the theory. And you find that there is a massless spin 0 particle, which is your Goldstone boson. So the presence of a Goldstone is actually implied just by these anomaly equations. So we're going to see a similar thing now for linearized gravity and spin 2. Okay, so now going to linearized gravity. So we have this Weyl operator, and this Weyl operator satisfied 2 different conservation conditions. It satisfied conservation and dual conservation. So we have to ask, can those be maintained at coincident points in the same way, or is there an anomaly between them like we had for the simple example just now? So let's look at the 2-point function for the Weyl operator now in momentum space. So we can compute this from the linearized action, and we get some non-local part, which is completely fixed. So it has this structure here. So all of this has dimension 2 in momentum space. So the non-local part looks like 4 powers of p over p squared. But then there are possible local contact terms we can add. And then there are 2 possible contact terms that are consistent with the symmetry, the index symmetries of the Weyl tensor and the tracelessness and all that. So C1 and C2 parameterize these 2 possible local contact terms. So now we impose the conservation equations, and we get some failure, which depends on these coefficients C1 and C2. And as expected, the failure is local in momentum space, so it's happening only at coincident points. So now we can ask, is it possible to maintain one or the other of these? So we can ask, can we impose exactly the conservation equation? And you can, and that fixes the C1 and C2 coefficients. And then there's no freedom left, and the dual conservation just fails with some fixed coefficient here, which is the anomaly coefficient. So there's an anomaly here, which is the failure to be able to have both conservation and dual conservation at the same time. Here's what it looks like at the level of the effective action. So if we want to find the effective action for this linearized gravity, we should couple the Weyl operator to a background gauge field, which has the same symmetries as the Weyl operator. So here's our linear Weyl operator now being coupled to this gauge field A. And this gauge field A has it's now a 4-index gauge field with the same symmetries as the Weyl operator. So here's the action now. Here's the first line is the original linearized Einstein-Hilbert action. The second line is the coupling now of the Weyl tensor to this operator A. So this first part is the two derivatives on H making the Weyl tensor, and then the index symmetries of A ensure that this has the right symmetries that this is actually just the Weyl operator. And then we have to include all the possible local counterterms involving this external gauge field that have the correct dimension. And there's two of them, which is correct because there were two possible local contact terms that you could add to the correlator. So these are the two possible local counterterms. So now we can try to impose the gauge symmetry corresponding to conservation on this effective action. So if I have conservation of W, the gauge symmetry that I'm going to be looking for is some derivative of some gauge parameters, which has the mixed symmetry indices of a hook-shaped tableau like this. So this is, if I plug in this gauge variation for A, integrate by parts onto W, that will ensure this conservation condition. So I'm looking for this gauge symmetry in the action. The graviton may also transform, so I have to write down the most general possible way that the graviton can transform under such a gauge transformation, and that's what this is with some arbitrary parameter B. So now we try to impose the gauge symmetry. So something different happens in dimension greater than 4 versus dimension 4. So I'm going to start just with dimension greater than 4. So in dimension greater than 4, everything works. I can impose this invariance, and it fixes everything. It fixes these two coefficients C to be these things, which blow up in D equals 4, which tells you something different is going to be happening there, and fixes the gauge transformation of the graviton. So now everything's fixed, and now we can just look, is it also dual conserved? And the dual conservation would amount to some gauge symmetry that looks like the derivative of some 5-index gauge field with these symmetries. And this now fails, and the non-invariance gives some anomaly equation, which is now completely fixed. So now we can run this argument backwards as well. We can say, suppose I have some theory with a operator with the symmetries of the Weyl operator that satisfies this kind of anomaly equation. I can prove a massless spin 2 version of the Goldstone theorem. This anomaly equation completely fixes the 2-point function between these W's, and then by looking at the spectral decomposition of this 2-point function, you can show that there has to exist a massless spin 2. So you can think of the graviton as a massless spin 2 Goldstone theory of the anomalous generalized symmetry. Okay, so let's go back now to D equals 4. So in D equals 4, we failed. We can't impose the conservation or the dual conservation. In fact, we can't impose either of them in D equals 4. So something different is happening here, and what's happening is that it's similar to what happens in two-dimensional field theories when I look at the stress tensor. So if I have a two-dimensional conformal field theory, the stress tensor is supposed to be traceless in a conformal field theory, but we know that you cannot, if I try to look at just a traceless symmetric tensor and I look at the 2-point function and I try to impose exact conservation at all points, because a stress tensor is supposed to be conserved everywhere, you can't do it. And you in fact have to include a trace in the stress tensor. And this is the trace anomaly in 2 dimensions. So in 2 dimensions, the true stress tensor has a traceless part, which has non-local correlators, but it also has a scalar part. And the scalar part has purely local correlators with everything else. So all its correlators are contact terms. But by choosing its contact terms properly, we can make the TAMU conserved everywhere. So that's the trace anomaly. It's a trade-off between making the stress tensor exactly conserved everywhere versus exactly traceless everywhere. So a similar thing is happening in our linearized gravity. The Weyl tensor is traceless, but in order to make it conserved, we've got to relax it being traceless. So we're going to go back to the full Riemann operator, which includes now the traces. So the Weyl operator is the traceless part of Riemann, but there's also the Ricci tensor, the traceless part of Ricci, and the Ricci scalar. So we can add back in these trace components and consider the full Riemann operator. And we can demand that these trace components have purely local correlators with each other and see if we can make the Riemann operator conserved. So this is now it's a new kind of trace anomaly, if you like, where the trace of the Riemann operator has to be non-trivial. Okay. In D equals 4, we should also worry about, we have this kind of electromagnetic duality at play. If I look at the dual of the curvature, the Bianchi identity that the curvature satisfies is the same thing as the traceless condition of the dual curvature. So if I'm going to relax tracelessness to be consistent with duality, I should also relax the algebraic Bianchi identity. So I should allow other components into the curvature that come from not requiring this Bianchi identity. So really, we should consider a curvature which has just that's only anti-symmetric in the first 2 and the last 2 indices, that doesn't have the full symmetries of Riemann. So the symmetries of the objects the object that I'm considering is just 2 pairs of anti-symmetric indices, and then the various irreducible components of that are these things all shown here. So here's the original traceless Weyl tensor. Here's the traceless part of the Ricci tensor. Here's the Ricci scalar. And then there are these other mixed symmetry components that come from relaxing the Bianchi identity.
These are like torsion contributions.
I don't think it's torsion, because torsion is just one derivative of the metric, whereas these are all still things that are like 2 derivatives of the metric. So these are like I guess, yeah, if you had torsion, you'd have these components here.
I'm just thinking like the torsion conservation equation is precisely the right-hand side of that top equation.
Yeah. Okay, so yeah, if you have torsion, yeah, that's right.
Okay.
Yeah. Okay. Yeah. So we're going to allow these other components, which, yeah, I guess you can think of as coming from torsion. And we're going to demand that all these other components have purely local terms and ask, can we impose conservation and dual conservation on this R object? Okay, so here's what happens in summary. So we have these 4 different conditions that we're asking for: tracelessness, dual tracelessness, which is the algebraic Bianchi conservation, and then dual conservation, which is the differential Bianchi. And we're going to ask what combination of these 4 things can we impose at the same time. So when we go through the algebra, we find that any one of these you can impose, no problem. If you want to impose 2 of them, you can do that in most cases, except for if you try to impose conservation and dual conservation, you can't do it. So you have to relax some of the tracelessness. You can't do this with just purely traceless stuff, which is why in the effective actions we found these 1/d-4s, because we were assuming a priori that this thing is traceless. So if you wanted to write an effective action for this, you'd have to write additional background gauge fields for the trace components of the curvature tensor. And then 2 is the best you can do. You can't impose any 3, you can't impose all 4. So that's the structure of this anomaly. In dimensions greater than 4, it's slightly different, because it doesn't have to be consistent with, there's no electromagnetic duality anymore. So in D greater than 4, we can impose any 1. We can impose most sets of 2 except for conservation and dual conservation, which we saw already. And in this case, there's one we can impose 3, which we saw, well, this we saw from the effective action, that we could impose tracelessness, dual tracelessness, and conservation, but any other combination we can't impose. So that's the structure of this anomaly in dimension d greater than 4. All right, so I should wrap up. So I think in summary, there's still much to explore even about the IR fixed point of quantum gravity. So most people who do quantum gravity are worried about the UV fixed point and the mysteries of quantum gravity, but I think there's still a lot to learn in the infrared where we should know everything. So I've shown you here some of the first steps in that direction, the conformal symmetry, these one-form symmetries, new types of anomalies among them. The really interesting question is whether any of these structures which we've seen just for the free, exact IR fixed point, whether these things can say anything beyond the fixed point. Can you say anything about the RG flow as you move away from the fixed point and into full nonlinear general relativity? Does any of this actually hold? So, there's some reasons to think that it might. The fact that these charged solutions exist nonlinearly, it may be that the structure is such that it doesn't exist, in the bulk nonlinear, but that it all becomes some sort of asymptotic stuff that you have to worry about, because we know that in full general relativity, you can't localize energy. There's no localized operators. You have to talk about asymptotic energy type things. So maybe it kind of all gets pushed to the boundary in some way as you try to go beyond the linear fixed point. But exactly on the way that occurs would be interesting. And there's also even thinking about what it means to deform away from the IR fixed point to nonlinear gravity. It's different in some sense of gravity. So usually if I have an effective field theory, I think of deforming away from the fixed point as certain irrelevant operators that I add in, which kind of tell you about the flow coming in to the fixed point. So like the chiral Lagrangian in CFT, for example, there's irrelevant operators you can add that tell you about how you get back to the fixed point. But here, as a conformal field theory, it's, if I'm thinking of this purely as a conformal field theory where the local operators are just these W's, naively, what I would try to do is start adding irrelevant operators, which are like W squared and W to the 4th and various irrelevant operators like that. But that's not what GR is. GR is not just a deformation of the free theory by some Weyl operators. It's something else. The gauge symmetry is being deformed. It's something more complicated. So to understand what that is in the language of just deforming a free CFT would be interesting to understand. And then of course there's the question about higher spins, how all of this extends, how these one-form symmetries, anomalies, and so on. There should also be a similar story for all the higher spins, and maybe even nonlinearly for Vasiliev-like theories. All right, so I'm just about out of time, so I'll stop there. Thank you.
So is there any question from the room?
Yeah, I have a question. Can you hear me?
Yeah.
So in all the examples that you talked about in the anomalies discussion, it seems like you are always sacrificing the dual conservation equation. Is there a deep reason why? Because that seems to come from the Bianchi identities, and is there a reason why?
No, I think that's just, you could have done it the other way around.
Okay.
So that's usually a physical question, which current do I think is actually exactly physically conserved and which isn't. But from the point of view of just the structure of the anomalies, it doesn't matter. You could have done it the other way.
I see. So you are not proposing any partiality for one symmetry or the other, right?
Yeah. So like in these pictures here, this tells you about all the possibilities.
Okay.
So I can ask a question. So the one-form symmetries that you talked about corresponding to the solutions, are there anything analogous to higher form symmetries in GR?
Yeah, there should be. There possibly could be, because this Weyl operator, it has mixed symmetry. So there might be some, I didn't have to contract this thing with a killing vector to make just one form. So I could have just left it as a Weyl operator and asked, what is this thing as a symmetry? What is this 4-index thing with the symmetries of the Weyl as a symmetry? What kind of object does that thing couple to? So that's an interesting question that I don't know the answer to. I don't know what is the natural object or type of symmetry which has as a current something with the symmetries of the Weyl tensor.
So we don't have any idea what sort of, I mean, how would the solutions look like?
Yeah, I don't know what those are. That's a good question.
Would it have to be some sort of extended object with those?
Yeah, it would have to be some kind of extended object, maybe with other things embedded in it, because yeah, it's not just an extended object, because extended objects always couple to purely anti-symmetric form fields. So it has to be some other structure that has this mixed symmetry index stuff built in.
I mean, is it possible that in higher dimension you can have, like black strings corresponding to solutions of these higher form symmetries?
Yeah, so in higher dimensions, you'll have black strings, you'll have you have these Taub-Nut, higher codimension Taub-Nut type charges. That's all still, though, corresponding to these form symmetries, because these are all still just extended objects that couple to anti-symmetric P-form types things. So this really has to be something different.
Okay, any question from online?
I have perhaps a dumb question. Is there an easy way to understand why D equals 4 is consistently special?
Yeah, I don't know. I mean, I don't know if I have a good answer to that, other than, I mean, it's kind of the lowest dimension in which all this stuff happens without being trivial. And the lowest dimension stuff tends to be degenerate. That's kind of the only intuition I really have. Yeah.
Is there any sort of if I was just thinking because of the duality of the curvatures that you were talking about. I mean, I imagine there's some sort of story I could formulate this with, like the dual graviton.
Yeah,
that's formulated in a parallel way.
That's right. Yeah, so you should be able to write an action for the dual graviton in the same kind of way, and all this would go through just with W and W tilde interchanged.
Okay.
Yeah.
Okay. All right. Thanks.
Right. So if there's no more question, let's thank the speaker again.